So for synchronization of concurrent processes, ensuring mutual exclusion is a fundamental requirement. However, remember that achieving mutual exclusion is not the only concern. The bounded waiting requirement is also crucial, and actually this set test and set instruction uh, usage, we found problems not only about busy waiting, but also failing to meet the bounded waiting requirement. So let's look at this algorithm. It uses the test and set instruction in a different way to achieve all requirements in this time, all requirements of critical section problem solution. Okay, so let me explain how this algorithm works. So first, each process maintains a Boolean variable array called waiting, and where each element represents the waiting status of a process. And initially, all elements of waiting array are set to false. So all elements of this array is initially set to false. And also, we have Boolean, oops, e variable is also set to false. So these structures are used to coordinate processes and control access to critical section. So to prove that the mutual exclusion requirement is met, we note that process PI can enter its critical section only if either waiting I is false or key is equal to false. The value of key can become false only if the test and set is executed, and the first process to execute the test and set instruction will find key false. So all others must wait. The variable waiting I can become false only if another process leaves its critical section, and only one waiting I is set to false, maintaining the mutual exclusion requirement. To prove that the progress requirement is met, we note that arguments presented for mutual exclusion also apply here, since a process exiting the critical section either sets log to false or sets waiting j to false. Both allow a process that is waiting to enter its critical section to proceed. And lastly, to prove that the bounded waiting requirement is met, we note that when a process leaves its critical section, it scans the array waiting in the cyclic ordering. Okay. So it designates the first process in this ordering that is in the intersection as the next one to enter the critical section. Any process waiting to enter its critical section will thus do so within n-1 turns. Thus, every process that is waiting to enter the critical section will do so within a finite predetermined number of turns, and it guarantees fairness and also prevents any process from being indefinitely postponed. Yeah, so hardware solutions also come with notable disadvantages. Firstly, processes waiting for access to critical section continues to check for availability, and this results in them consuming processor time even when they are not actively executing any useful tasks. Okay, so which we call this negative effect as busy waiting. And also, if multiple processes are waiting to enter the critical section, there is a possibility that a particular process might never get a chance to execute if others repeatedly acquire the critical section. This situation where a process is delayed is known as starvation. And while these instructions can ensure mutual exclusion, they don't guarantee a bounded waiting requirement. So processes waiting to enter a critical section might have to wait indefinitely before getting their turn, which doesn't meet the requirement of bounded waiting in the critical section problem. So in summary, special mention instructions, although effective in providing mutual exclusion, but they fall short in addressing issues related to CPU utilization, potential starvation, and ensuring a fair waiting time for all processes.